Hello, everybody. I think we've just just gone live. Now I'm just going to briefly overview what I did before, but later on you can watch the stream using the recording, and then you could view the first part of this in a bit more detail. But basically, we're going to be going over numerical methods today. Now it's a sort of mix between Math2089 and Math2301. So we're sort of trying to account for both, but it will be more on the Math2089 side of things rather than the Math2301. So we're sort of focusing more on the computational side rather than the more theoretical side that's looked at Math2301. But the first topic we were looking at was floating point arithmetic, so storing numbers in floating point. Now we're just overviewing big O notation and flops. So when it comes to big O notation, it sort of tells us how sequences grow. And essentially what it's saying is that given two sequences, we can say that one sequence is big O of another sequence if for some large enough number, every single value in this sequence is less than some constant multiple of the value in the other sequence. Now, it's really useful for classifying algorithms based on their response to changing input size. So, for example, an algorithm that is O of n would respond a lot better to larger inputs than an algorithm that's O of n squared, right? You can see that O of n is bounded by a linear function versus O of n squared is bounded by a quadratic function. Now, a flop is a floating point operation. So that's any multiplication or addition of floating point numbers. Now, flops can be used to measure the computational cost of an algorithm. So if we know some algorithm and then we know roughly how many flops it is, then we can sort of estimate the computational cost of it. So now we're just going to be looking at this question from a past paper. So that's, what is the output of the following MATLAB commands? Well, we know that infinity minus infinity, well, that should give us not a number. And epsilon 3 plus 3 greater than 3. So this is asking whether this statement is true or false. Now we know that epsilon of 3, right, is the gap between 3 and the next largest machine number. So clearly we can see that epsilon of 3 plus 3 should be larger than 3, right? Because we know that the next largest machine number is equal to 3 plus eps3, right? So we can say that this will be true, and that will give us a truth value of just 1, and that's what MATLAB would output. Okay, so now we're going to be moving on to linear systems. So the first thing we're going to be looking at is LU factorization of matrices. Okay, so how this works is given some n by n matrix, right? And we have all non-singular submatrices. So the principal submatrix is just going to be the top left submatrix. So if I have a matrix like this, right, 0, something like this, we're going to be getting that these are our principal submatrices. So as long as they're all non-singular, so that's related to having a non-zero discriminant, we can say that there exists a factorization in terms of a unit lower triangular matrix, L, and a upper triangular matrix, U. So what a unit lower triangular matrix is something that has ones along the diagonal, only zeros on the upper half of the diagonal, and then we can have entries below that. So this is our unit lower triangular matrix, and U is our upper triangular matrix. So that just means it's non-zero above the diagonal, and it's 0 below the diagonal. So we could have something like 7, 3, 2, 1, 8, 4, and only zeros below the main diagonal. So these two matrices would form an LU factorization of some matrix A. Now we know that if this factorization does exist, then it's unique. Now, how do we actually find the LU factorization? Well, a lot of the time we can just use computer software to find it, but essentially what we want to be doing is expressing L like this. Let's say L21, L21, sorry, L31, L32, and then letting U equal something like U1, U2, etc. Right? So we need to actually have these values here and then multiply and solve. But the benefit of actually finding an LU factorization is once we find an LU factorization, it's very easy to solve a linear system. So I'll give you an example, right? So suppose we're trying to solve this linear system, AX equals B. Let's suppose that we know that A equals LU, then we can write it as LUX equals B. Now we're just going to do a little substitution. We're going to say UX equals Y, okay? And then we have another equation, LY equals B. So what we have is we've sort of split this linear system into two component equations. But the benefit is that each of these equations is very easy to solve. You can see that if I had for example, upper triangular matrix, we'll start off with Ly equals B actually. So we'll start off with the lower triangular matrix. So to solve something like this, remember our lower triangular matrix will look something like this. 4, 3, 2. And then we are solving this equals some B1, B2, B3. We can see that what essentially we're going to be having is three different simultaneous equations, right? We're going to have something like y1 equals b1, and then 4y1 plus y2 equals b2. But you can see that what we can do is something called a forward substitution. So we immediately know the value of y1. Okay, we know the value of y1 because of these zeros here, means that it's just equal to b1. And then what we can do is substitute that value into the next equation, solve for y2, and then sub those two into the last one, and we can solve for y3. So it's a very straightforward process of forward substitution. Now, what about the other case? What about solving ux equals y? Well, once we've solved ly equals b, we know the value of y, then we can solve ux equals y. And this case is, instead of having a lower triangular matrix, now we have an upper triangular matrix. But what we can just do is a back substitution. So it's very similar to solving systems that we looked at in first year. We can just do a back substitution to get our values. So to solve the linear system, it's a matter of finding the LU factorization and then just a forward substitution and then a back substitution. Now, something we do need to go over is permutation matrices. So essentially what's going on is we may not be able to find a LU factorization if this condition doesn't hold, right? If the condition, the leading principal submatrices are non-singular, right? Suppose we had a non-singular principal submatrix. In that case, what we can do is reorder the rows to ensure that all of the principal submatrices are non-singular. So what that means is to actually reorder the rows, that doesn't change the solution to the system. Because at the end of the day, right, if we have a system of linear, simultaneous equations, the actual way that we label the equations is arbitrary. So as long as we reorder the rows, we don't change the solution to the system. However, reordering the rows may allow us to find a new LU factorization. So that's what a permutation matrix is used for. So that allows us to reorder the rows. And then we just need to keep that into account when we're doing these forward and back substitutions. Now, something important to look at is the cost of factorization. So in this case, how many flops does it take to actually find an LU factorization? The answer is it takes 2n cubed over 3 plus O of n squared flops, okay, which is roughly equal to just 2/3 n cubed flops for large n. Okay, so that's how many floating point operations it takes. Now, when it comes to actually solving the linear system, so not only factorizing, but also finding the forward, actually doing the forward and back substitutions, those add an extra, well, n squared flops. So the total cost will be 2n cubed divided by 3 plus O of n squared flops. So now we're going to be looking at another type of factorization, the Cholesky factorization. So in a special case, so this is not every single scenario, we may be able to find a Cholesky factorization. So it's important that we look at the conditions for a Cholesky factorization. So first of all, Cholesky factorization is unique when it exists. Now, the conditions required is that we need a positive definite and symmetric matrix. So remember that symmetric means that the matrix is equal to its own transpose. What about positive definite? Well, positive definite is related to having positive eigenvalues. So dealing with a symmetric matrix, if we know that the matrix has all positive eigenvalues, then it is positive definite. So now, in terms of a Cholesky factorization, what exactly is it? Well, it's a factorization of the form R transpose times R. Now, R is an n by n upper triangular matrix, okay, the same as what we had in that LU example, but only positive values inside. Now, R transpose is going to be a lower triangular matrix. So what we have is, again, a lower triangular matrix and an upper triangular matrix multiplied. Well, this is very similar to the LU factorization. What's the point? Well, you can see that the cost for a Cholesky factorization is actually only n cubed over 3 flops. So that is actually half that of the LU factorization. So the benefit is that it's less computationally costly. However, it can't be used in every single scenario. So now let's look at actually solving the linear systems. Well, it's very similar, in fact, almost exactly the same as the LU factorization, because remember, R is an upper triangular matrix. So to solve something involving R, then we need to use back substitution. And now RT is lower triangular. So that means we can use forward substitution to solve something involving RT. So now the total number of flops required to solve a linear system, so that is not only the Cholesky factorization, but also forward and back subs, it's going to be something that is, well, n cubed over 3 plus O of n squared. So you can see it's roughly half the number of flops as LU. So now another definition we need to look at is sparsity. So sparsity is dependent on the number of zero and non-zero elements in A. So, given some matrix, in a lot of the cases we're working with very large matrices. The case is there will be a lot of zeros throughout the matrix. Okay, so the density of these non-zero elements throughout the zeros is the sparsity. Now, the reason why we're interested in sparsity is that sparse matrices, those are matrices with very high sparsity, are a lot easier to work with when it comes to actually computing, say, their matrix product or calculating the factorizations. So it's easier to work with sparse matrices. So now we're going to be going over a bunch of definitions that will help us look at the sensitivity of linear systems later on. Now, a lot of this stuff is very relevant for Math2089 as well, because in Math2089 you may be asked to prove stuff about vector norms and so forth. But what exactly is a vector norm? Well, it's a sort of extension of the idea of the length of a vector into a more generalized idea. So what's going on is we need some norm that is an operation on a vector to have the following properties. So it needs to be always non-zero, and it can only equal 0 when we're dealing with the zero vector. Now, it must satisfy the triangle inequality. So that means actually satisfying this inequality here, and we also need to be able to sort of bring out a constant to the front, if that makes sense. So Now let's look at the most common example of a norm, and that is the vector p norm. So the vector p norm is sort of described here. Now we're not going to be working with the generalized p norm very much. We're going to be looking at specific examples of p norms. So that's the vector 1 norm. So the vector 1 norm is the sum of all the absolute values of the components. The vector 2 norm is actually the exact same as the normal Euclidean distance. So this is what we normally use to find the length of a vector. And then there's the vector infinity norm, which is the vector infinity norm is just the maximum component of the vector across all its indices. Now, we're going to be looking at matrix norms. So what we just looked at is a vector norm, but a matrix norm is very similar. So it's an operation on a matrix which has the exact same properties. Okay. Now, a consistent matrix norm is one that satisfies this inequality here, which is a sort of extension of the Cauchy-Schwarz inequality. Now, the reason why we're looking at matrix norms is that they'll help us out soon enough. But when it comes to actually calculating matrix norms, this definition doesn't help us a lot. So this is the formal definition of the matrix P norm. However, the definitions that will help us a lot when we're actually calculating stuff is these. So to find the matrix 1 norm, it is simply the maximum column sum. So this formula is quite confusing, but essentially, if I have a matrix, right, what I want to do is sum all the absolute values of the elements on the columns, add them all together, and the largest column sum is the matrix 1 norm. Now, what I can also do is determine the matrix infinity norm. So to do that, it's the maximum row sum instead. And the matrix 2 norm is the square root of the largest eigenvalue of the matrix A transpose A. So the most common will actually be asked to find are these two. So now, the reason why we're bothering with matrix norms in the first place is that they're going to help us when it comes to finding condition numbers. So first of all, we're dealing with non-singular matrices. That's what we had earlier when we're dealing with the LU factorization. That is essentially, we're dealing with non-zero determinants. So it's an invertible matrix and all non-zero eigenvalues. So the condition number is defined as this product here. So the product of the norm of A and the norm of A inverse. So oftentimes we'll need to be specifying condition numbers with respect to a certain P norm. So for example, this would be the 2 condition number of the matrix A. Now with real numbers, we'd expect this product to equal 1. But with matrices, it's not necessary that it equals 1. In fact, we can see that it should equal 1 for the identity matrix. However, for all consistent matrix norms, we expect it to be greater than or equal to 1. Now, a matrix is said to be ill-conditioned if it has very large condition number. So large, this is essentially saying large condition number means it's ill-conditioned. And we'll see what ill-conditioned means soon. But another important part of this slide is actually calculating the 2 norm condition number. So to find the 1 norm condition number and the infinity norm condition number, what we can just do is actually use this here because it's very easy. It's very easier for us to actually calculate the condition number, the matrix 1 norm and the matrix infinity norm, but it's a bit harder for us to calculate the matrix 2 norm. But we can calculate the condition number using this here. So this is quite confusing, but it's essentially saying largest positive or largest absolute value of the largest eigenvalue divided by smallest eigenvalue. Okay. So now let's look into an example of actually calculating condition numbers. So to calculate condition numbers of these ones, like I said, if we're looking at the 1 and infinity condition numbers, what we should just do is calculate the matrix norms. So let's start off with infinity. So I know that the kappa of the condition number of the infinity condition number of A is equal to the infinity norm of A and the infinity norm of A inverse. So they give us A and A inverse. Now we just need to calculate the maximum row sum, I think it was. So just looking back, it's the maximum row sum, yeah. So what we're just going to do is calculate the row sums. So the sum of row 1 is 2 plus -1 plus 2. That gives us 5. We can see that 2 should give us 3, and the third row should give us 6. So now we look at the largest one, and the largest one is 6. That implies that the matrix 1 norm, so the matrix infinity norm of A equals 6. Now we can do a very similar process with A inverse. What we should get is A inverse has an infinity norm of 4. Okay, so you can see that as we sum all the rows, the largest row would be this one, has 4. So now that makes the infinity condition number just equal to 4 times 6 equals 24. So you can see to find the condition number with respect to the 1 norm of A, it'd be a very similar process except we'd find the column sums. And if we did get that, we should get some answer. I'll put the answer on the slides later on. So now the whole reason why we bother with condition numbers is to deal with sensitivity of a linear system. So this is related to the amount of error we get when we solve a linear system using a computer. So remember from floating point that most numbers that we have in a computer are approximations. Okay, and to quantify the error, what we want to look at is the relative error. So the relative error, we're calling, I think it's a bit easier to just call it EX, so epsilon X and epsilon A. So this is the relative error in X. So relative error is just going to be the difference between X and its approximation. So that's the actual value of X, actual X, and that's the approximation in X. Okay, so now we divide that by the norm of actual X, and that gives us our relative error. Now it's very similar for the relative error in A. We look at the norm of A minus the approximation in A, divide that by the norm of A. So now we have these notions of relative error. The question is, if I have some linear system, so I have a linear system AX equals B. Let's say I know A and I know B, but I only know them to a certain amount of precision, limited by the computer. So I know A and B, and we have values A and B bar, which are approximations. The question is, how far off is the solution to this system X bar from the actual value X? So, i.e., what is the error, or the relative error in X if I approximate A and B as A bar and B bar respectively? So to do that, that's where our condition number comes in. We have this theorem here that says that the relative error in X, so that is the solution to the system, is roughly equal to the condition number multiplied by the sum of the relative errors. So this is just the sum of relative errors. And that's our condition number here. So we sum the relative errors and then multiply by a condition number, and that gives us roughly the relative error in X. So you can see that the reason why they're called ill-conditioned matrices, if they have high condition number, is that as the condition number becomes larger, we expect the error in X to increase. So what we want to deal with are matrices, ideally, that have lower condition numbers. So now, when it comes to these relative errors, if we know A or B exactly, then the relative error is 0. Now, if we know some value to k significant figures, then the relative error is bounded by 0.5 times 10 to the negative k. So that's important. So that will help us. So if we know it to k significant figures, say we've got measurements from an experiment, then we can use this as an upper bound on the error. So now let's look at an example of a question to see where we can put all of this into practice. This is from a past 2089 exam. So let's suppose we have some MATLAB code and we've got this output. So we have some matrix A and we have this output. Now, the first question is A symmetric? So is A symmetric? So looking at this information here, we know that this CHK1 is equal to the norm of A minus A dash, and that's the 1 norm. So that is equal to the 1 norm of A minus A dash. Well, what is A dash in MATLAB? That is the transpose. So what we're looking at is this. And we know that this is actually quite small. So it's something like on the order of 10 to the negative 15. So because it's very small, we can say that A is approximately A transpose, and this approximation has very small error. So remember that the norm of a matrix can only equal 0 if that matrix equals the 0 matrix. So that's sort of how we can make this deduction. So now we can say that therefore A is symmetric. So we know, yes, A is symmetric. Now what about positive definite? So remember, when we're dealing with a symmetric matrix, positive definite comes from the sign of the eigenvalue. So are they positive, negative? We can see that we have the list or the maximum minimum eigenvalue. So the minimum eigenvalue is this value here. That's actually positive. And well, the max eigenvalue is obviously larger than that. So we have positive eigenvalues. So therefore, it is positive definite. So now, continuing on, calculate the 2 norm condition number of A. So how do we calculate 2 norm condition number? So remember that the 2 norm condition number was equal to the absolute value of largest eigenvalue divided by absolute value of smallest. Okay, so in this case, that is 9.121 times 10 to the 3 times 10 to the 4, divided by 4.107 times 10 to the 2. So that's going to give us something on the order of 10 to the 6. So that's our condition number. So now, the next part of the question is, suppose we know A and B to 6 significant figures. So that means that the relative error in A is less than or equal to 0.5 times 10 to the negative 6. And the relative error in B is, again, less than 0.5 times 10 to the negative 6. So that means that the relative error in X is approximately equal to, remember, the condition number of A times EA plus EB. And we can say that that will be less than or equal to our condition number, which is 2.02 times 10 to the 6 times 0.5 times 10 to the negative 6 plus 0.5 times 10 to the negative 6. And that should give us something like 2, equals to 2. So we can say that the relative error in X is approximately 2. So now, let's suppose that we did have a Cholesky factorization of A. Explain how to solve the linear system AX equals B. Remember that given some Cholesky factorization, what we can do is say AX equals B. That now equals RT equals B. Now we have to do the substitution. So we need to say Rx equals Y. And that means we have RTY equals B. So now these are our 2 equations. So now how do we actually solve the linear system? Well, we solve this one first. To solve using forward sub. So the reason why we're using forward sub again is that RT, that's R transpose, is a lower triangular matrix. So we use forward sub. And then solve this one, solve using back sub. And then we'll be done. So that's how it's done. So I've finished off now for linear systems, and I'll be handing over to Anne, who will cover the next 2 topics.
Okay, I just want to test whether my audio is working first. Um, okay. Um, Lucky, does my audio seem to be working? Okay. I am just going to hope that my audio is going well. Just because I did have a few audio issues. Um, when I was setting up stream the other day. I will keep an eye on the chat in case my audio is not working. But yeah, so I'm going to be covering our least squares problems and also our polynomial interpolation, as well as nonlinear equations. And I'm not sure whether the stream like started on time or it cut out the earlier section, but since we are covering both Math 2089 and Math 2301, there's going to be a few slight differences between the courses. I'll try my best to sort of point out those differences. But again, I'm not a lecturer, so I sort of just what I observed in the tests. And of course, whichever course you're studying, you should have a look yourself and sort of just, be confident in yourself as well. So when it comes to least squares problems, for those of you studying 2089, you would have been tested on both of these topics in test one, I believe. Either test, yeah, I think test one. So when it comes to the finals, there isn't as much of a focus on these two topics. So I'm gonna cover some sections a bit more briefly. And similarly with Math 2301, there's a bit of a heavier focus on the polynomial interpolation section. So to some sense, we're going to cover our least squares a bit broadly. So what are our least squares problems? And if I sort of just call it regression, it probably rings a lot more bells, or line of best fit. But essentially, these problems are when we have a bunch of data points, and the curve that we want to fit to it, the degree of this curve is less than the data point. Sorry, less than the number of data points. So for example, if I want like a linear line of best fit, but I've got, quite a few data points. And that's sort of different from polynomial interpolation, which is where we're actually forcing our polynomial to go through all of our data points, and we'll cover that in a bit. But if we just remember back to our least squares problems, this is going to follow on really nicely from what Locke was presenting earlier about linear systems. So if we just recall the two methods of solving our least squares problems, the first one is our normal equations, where we're sort of setting up this system of equations and solving that. And then there's also QR factorization, where we're solving sort of this system of equations. And sort of one thing that I also want to point out now is that both of them have very, similar computational costs, but there's various issues sort of with both of them. So just a sort of quick recollection of normal equations. What we have is A is our n by n matrix, and just to sort of remind you what's happening, and I might have to just make myself a new page here. Okay, wait, let's just see if that works. Okay, so A is our matrix here, 1, 1, 1, I'll just do dots. Oh, sorry, big mind blank just then. 1, 1, dot, 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 1. Over here is our x1, x1 squared, so forth, all the way to x1 to the power of n minus 1, because we're dealing with an n by n matrix, and then this would just be x2 and so forth, xm, and over here is xm n minus 1. U is our column vector here of our sort of coefficients. So A0, A1, all the way down to AN minus 1. And then we have sort of Y. And just for the sake of space, I am going to just write it as the transpose instead. So Y1 down to Y2, da da da, to YM transpose. Whoopsies. And the sort of system that we're trying to solve is AU is equal to Y, and of course, we'll sort of just fold those, make those vectors. So with and that's sort of just reminding you what was happening with this equation here. And with our normal equations, what happens is if we just multiply both sides by the transpose, we get this new matrix here, which is just going to call B. And what we notice about that is that it is both symmetric and okay, both symmetric and positive definite. Okay, I've just been told there's a bit of a issue with my screen. Okay, yeah, so since B is symmetric and positive definite, if we go back to what we were just covering earlier in linear systems, we can use Cholesky or LU factorization combined with forward and back substitution to actually solve that system. Now, the problem with this is since we're dealing with this new matrix B, and B over here is A transpose A, our condition number is going to be squared, and that's obviously going to be something that we have to check for. So we want to check that it doesn't get too large. And next we're going to just move on to QR factorization. So it's sort of a really similar process. This time, we're just going to write A instead as a product of two matrices. And I'm pretty sure, Lockie, you covered QR factorization earlier, so this should look quite familiar. And the good thing about using QR factorization is now the condition number is actually not going to be squared anymore, so we'll still be dealing with the condition number of A. However, QR factorization is a bit more computationally costly than Cholesky or LU factorization, especially because Q is rarely sparse. So what that means is Y isn't sparse. And just to remind you again, with QR factorization, this is the sort of system of equations that we have to set up and solve. But generally speaking, there shouldn't be too many questions on least squared problems, so I'm going to just sort of move on now to polynomial interpolation. And okay, that looks good. So yeah, polynomial interpolation now is when we have a certain number of data points. So let's say we have 4 data points, and we actually want to go ahead and force our interpolating polynomial through all of those data points. And one thing to sort of point out is that if you have n data points, so 4 in this case, the interpolating polynomial is going to have degree n minus 1. So in this case, we have a cubic interpolating polynomial. And that's going to carry across to everything. If you have 10 data points, you're going to have a polynomial of degree 9. Now, most of the questions that you'll have to answer, just because it gets really tedious, we normally are given 45 data points at least in MATH2089. And what I have here in green is just how we go about getting that interpolating polynomial between 2 points. And one thing that is sort of, Math 2089 exclusive, I don't believe it's covered really in MATH2301, is sort of using MATLAB to find our interpolating polynomial. So, let's say we have n plus 1 data points. So the general form of our polynomial is going to look something like this. One thing that you have to be familiar with in Math 2089, which I believe should have been tested in test 1. So again, I haven't seen too much of these in the past finals, is where you just have to set up your system of equations, which is quite similar to, this one up here. sorry, this one up here, and then use backslash in MATLAB to solve for those coefficients. We're not going to cover that too heavily right now. We do have past revision seminars, which were 2089 exclusive, that go into that in a bit more detail if you're a bit rusty on that. But what we are going to cover is our Lagrange interpolating polynomial. And what I have here on the screen is the formula for our Lagrange interpolating polynomial. So given n plus 1 data points, the first thing that we do is we write our Lagrange polynomials, and they sort of have this form. And one thing I just want to point out here is if you have a look at all of these guys here, these are just our data points, and what this really means is that all of this is done just by manual substitution. So it can get a bit tedious depending on how many data points you have. And when we go through our example on the next sort of few pages, you're gonna kind of see how tedious it gets. And then over here, we have our interpolating polynomial, and we have this guy over here is the formula for that. So it's just a lot of sort of substitution that we're doing here. So we're going to go ahead and look at a past Math2089 question. And the question that I have here is from 2019. But something that I've noticed is that this gets tested quite frequently throughout the years. You know, a question in a very similar form to this. So it will be really good to get familiar with it. So again, with these questions as well, you'll always be given like a set of data points to work with. In this case, we have 4 data points. So let's just go ahead and do our Lagrange interpolation polynomial. And just a quick reminder, here's the formula we're working with. And you know, this might look slightly, it honestly, personally, I think it looks slightly a bit too complex for what it actually is. Because you'll see in a moment when I just show you. Let's go and do the Lagrange polynomial. Oopsies. Okay, wait. I need to resize this rectangle, not move it. There we go. So we have 4 data points. So our Lagrange polynomials are gonna be around x1, x2, and x4. So if we just start off by looking at the Lagrange polynomial around x1, so the point 1, you're gonna see that it's actually quite straightforward. So basically, how I kind of look at it is you look at all the other points, and you sort of just manually substitute it into the formula. And this is sort of what we obtain for our Lagrange polynomial. And I feel like it is just a sort of a lot of manual substitution, so I might just go ahead and get rid of that. And give you guys a moment just to have a look at these. And you can kind of sort of observe sort of what is happening. So with the Lagrange polynomial around x2, which is this one here, we're just looking at all our other data points. So x1, x3, x4. And then of course on the denominator, we're doing 2 minus those data points. And likewise for 3 and 4. So one thing to point out is these Lagrange polynomials. If you're given, oopsies, that's not what I wanted to do. If you're given, you know, these 4 points, x coordinates, your Lagrange polynomials are going to actually just look the same. And of course, you know, that's going to apply. If you're given 5 points instead, the Lagrange polynomials will look different. If the space between the Lagrange polynomials is different, they'll change. But if you're given these 4 exact ones, they'll be the same. And then the interpolating polynomial, if we go up and sort of have a look at the formula again, what we're really doing is taking the sum of the function values at those points with the Lagrange polynomial. Sorry, the sum of all the products of the function values at the points, and then Lagrange polynomials. So I might kind of screenshot this and just drag it down so we have it on hand. Whoopsies. So these were our function values, and then our Lagrange interpolating polynomial is actually just that. So we're just taking, the function value over here, and that would be the coefficient of our Lagrange polynomial around x is equal to 1. And for those of you doing Math2089, I'm not sure that we actually have to go ahead. Let me get rid of this now. Go ahead and calculate the actual coefficients of these terms here. Of course, you can, where's my highlighter? You can go ahead and write it out fully. But, as far as I'm concerned, I'm not going to do that here. And I'm also not sure how necessary it is in an exam. So we'll just stick to this guy over here being our interpolating polynomial. So yeah, quite straightforward, just a little substitution going on. And then next we have our Newton form of our interpolating polynomial. And this formula over here looks a bit nicer than our Lagrange form. Now, the hard thing about the Newton form for the interpolating polynomial is there's a bit more work than the Lagrange form. So with Lagrange, we didn't have to do any extra work. We were just substituting, our points. We were given all of these numbers. We just have to do substitution. With Newton's form, we did have to do a bit of extra work in calculating these coefficients. And what these coefficients are our divided differences. And we use these square brackets to denote our divided differences. And the formula that we use to calculate those is given over here. Now, also a quick disclaimer here. Very important for Math2089. To be entirely honest, not quite sure how important this is for 2089. I know it was covered briefly, I believe, but quick note there, let's sort of move on. So also, this formula might look quite complicated. And one thing that you have to be able to do in Math2089 is to be able to prove or sort of derive the formula on your own. I do not recall off the top of my head because I won't be covering that today, but it has been asked in past exams how we sort of derive this formula. And they might not have this formula exactly, but they might ask you to, prove that f of x, the divided difference like this. Let me grab that up here. They might ask you to prove, sort of prove this formula here. x2, x3 minus fx1, x2 on x3 minus x1. So that's something that you should be familiar with. I'm not going to go through it today, as I said earlier, because it's a lot of it's just a lot of grunt work writing out formulas and rearranging them, and but essentially, all you need to consider is the polynomials about each of the points, right? So if we have 3 points, x1, x2, x3, we just want to consider the first order and second order polynomials around, x1 and x2. And I think that proof is a really good proof for you guys to work through before the exam. I think it also helps a lot working through it yourself instead of just having me write out a bunch of formulas and sort of do a lot of grunt work for it right now. But what we are gonna go on to is just a sort of practical example of finding the Newton form of the interpolating polynomial. Again, same question from before. So sort of same data points that we're working with, and one thing that we do when we're finding the Newton form is we construct what we call our divided difference table. So over here, I've got the numbers hidden behind this box, but we'll sort of just work through how we go about computing this table. And essentially what happens with our divided difference table is, in this column here, we're going to be, computing all the, how should I word it? The divided differences are sort of just two components, and then we're going to do that until we reach the last divided difference that we need. And if you just have a look at this formula here, you might be like, oh, what's sort of going on here? It's actually really simple. So all we sort of do for calculating our first divided differences is we take this value here and this value here. Okay, so I just do the calculations up here. So we take negative 1.802, my apologies, take the second value, so 1.0380 minus 1.8021. And we put that all on top of 2 minus 1. So again, sort of a lot of just number crunching in this section. And we're going to do, the same thing for this point here, change the wrong thing, this point here, and this point here, and then 4 and 3 as well. And what we're sort of going to obtain are these numbers here, and you can go ahead and also just do the calculations yourself and just convince yourself that these numbers are correct. Again, since the difference over here is only 1, we're really just looking at this number here minus this number up here. So it's quite easy to do. Now, second tier of the divided difference table, this time we're going to be looking at these values, and we basically follow the same procedure. So we're going to be looking at these two values here. Just this time on our denominator, we'll be doing 3 minus 1 instead of, 2 minus 1 or 3 minus 2. And how I kind of look at it is a bit of a shortcut, but like you kind of just look at where these numbers line up in terms of the x value. And this is sort of why we set up the divided difference table with these gaps, is because it works really nicely. So, for example, to compute that first divided difference there, we'll just do 1.0180 minus 0.7641 on top of 3 minus 1. So quite straightforward again. You should get these numbers here. And then we're left with one more calculation to do. And yeah, as you guessed, we're gonna just take this number here, this number here, and our denominator this time is going to be, well, it's going to be 4 and 1, so 4 minus 1. And if you go ahead and do that calculation, which I will just write out, and I'll also change my pen color back to black, 0.8238 minus 0.1270 over 4 minus 1. And the number that you should get is that. So I reckon go ahead and do those calculations yourself, just verify, all of the other numbers here. And when it comes to actually writing our polynomial now, the only values we care about are actually going to be this sort of top row over here. And this top row is going to be the coefficients of our Newton form of our interpolating polynomial. And again, this is just a bit of substitution to the formula, so have a look at this formula and be very comfortable with it. That is going to be our Newton interpolating polynomial, so you can kind of see those coefficients over here, 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 and here. Okay, so now we're going to move on to talking a bit about the interpolating polynomial error. So we have this theorem over here, and this is going to be relevant for both of the courses here, so 2301 and 2089. Now with 2301, you also want to be sort of familiar with, I guess, how this comes about, so the mean value theorem for our divided differences. So yeah, I guess the main difference between 2089 and 2301 is you really do want to be comfortable with the proofs and derivations in 2301. So yes, this is our theorem for our interpolating polynomial error. And what we can do to sort of minimize it if we want to, and we'll sort of look at that later with our Chebyshev points. I can never say that correctly. Is if we can minimize sort of this over here, we're going to be minimizing the error in our interpolating polynomial. But before we do that, let's just look at a sort of question that uses this directly, which again is going to be question 4 in this question here. And one thing I've actually forgotten to do is address question 3 as well, which I meant to do earlier, but I'll just sort of address it now. So is the Newton form of the cubic that we just wrote out earlier, so this guy over here, and is the Lagrange interpolation polynomial right over here, are they actually, let me go back to the question, are they actually the same polynomial? And the answer to that is actually yes, they are the same polynomial. And that's because when we're given these, 4 specific data points, and I am not plotting them in the right place, but the cubic that actually passes through them is going to be unique. And you can say the same for sort of any number of data points. So if you have 6 data points, the polynomial of degree 5, whether it's the Lagrange interpolation polynomial or the Newton form of that polynomial, they will be essentially the same polynomial. Now let's go back on track and I realize we're a bit low on time, so I might just move through a bit faster. So given this value over here, estimate the interpolation error, and sort of what we're doing in this question is we are just going to apply this sort of formula here directly. So we have a cubic, so obviously it's 3 plus 1, 4 times continuously differentiable. And what I might do is just go ahead, screenshot this, and then copy that down across onto this slide here. So you can sort of see how that lines up. Just for the sake of time, I might just go ahead and show you this instead of working through it fully. But essentially the error at the point 2.5 is now going to be bounded again. We can just see how this substitutes, how we get this substitution using the formula. Chuck all of that into the calculator, we're going to get 0.0586, and if you sort of want to verify that, feel free to do that as well if you'd like. And again, where we sort of get this 2.5 from is just on the question, in case you're wondering where that came from. Okay, so now we are going to move on to Chebyshev points, and I'm not going to cover it in too much detail, but essentially these are about sort of minimizing what I said earlier about minimizing this section in our interpolating polynomial error. And that way we can sort of just reduce our error. And essentially, it's just these formulas here. So you're going to set tj is equal to this thing here. And then you're going to set these nodes. So it's sort of just following the formula. And what really happens when we choose these points or these nodes is we just sort of minimize the oscillations at the end of our interpolating polynomial, and we reduce the error sort of that way. But I am going to move on, so we do have a few more topics to cover, so just gonna keep an eye out for that. So I'm gonna move on now to nonlinear equations. And what I'll be covering in this topic are just our slow convergence method, so bisection and fixed point iteration, as well as some of our faster convergent methods, so Newton and our secant method. So and I think for both of the courses, it's these four that are covered. So we have a sort of nice overlap happening over here. But yeah, so the problem that we're sort of just trying to solve is just our nonlinear equations. And we want to sort of solve for the zeros of our function here. And in some questions, you're going to need to rearrange your question to have it in the standard form. And we'll do an example of that down the line, I believe. Just covering a bit of notation. I'm not gonna go through this too much just because, some of these things like intermediate value theorem should have been covered back in 1A and 1B. But these are just some results that you need to be familiar with also if you want to be able to prove certain things. So I just showed them on the screen, and so we'll just move past that unless anyone has any questions, which I do not see, so I think it should be fine. Again, there's a delay. But let's sort of move on to going through our sort of methods, and I'm just gonna go over here. So with these nonlinear methods, they're what we call iterative methods. So basically, in most of them, we're going to have an initial guess, and then we're going to iterate from that point onwards. So we're going to, figure out x2, x3, and so forth, until xk. And once the error there is less than sort of our tolerance, we're just gonna sort of go with that. And one of the important things that we want to take away from this topic is our order of convergence. So our order of convergence is our largest value here, such that this holds. Yeah, so I was like, oh, I'm missing the absolute value sign. So yeah, you can see that here. And this beta here is what we call our asymptotic constant. You might also see it called our rate of convergence. I think it is more commonly referred to as our rate of convergence. And we're going to notice our different methods are going to have different order of convergences, which you also need to be familiar with. Yeah, so let's start off with our first method, which is bisection. And essentially, I'm sort of just going to go through the procedure of how to do it. But it is sort of just really following this procedure. So suppose that, we have f of a and f of b is less than 0. And essentially what that means is the signs are going to be different and we're going to have a 0 between that point. We're going to take the midpoint as our first guess. And then we're going to compute various things. So we're going to compute the value of the function at the midpoint. And if either one of these, whichever one of these conditions holds, we're going to, choose a new interval to sort of work with. And then we keep on iterating using that same process. And the order of convergence for bisection is we have linear convergence, and essentially what that means is our nu is going to be equal to 1, and our rate of convergence is actually going to be a half. And as far as I am concerned, I don't believe we actually have to go about proving these results, but I'm not sure on that point. Okay, so that's bisection. Next one is fixed point iteration. So fixed point iteration is also one of our other linear order of convergence methods. So again, our nu is going to be equal to 1. And essentially, we're going to choose a starting point and then compute our next guesses by evaluating the function at that starting point. And we're going to keep on doing that until our error becomes smaller than our tolerance. So also really straightforward there. And just on this note with order of convergence is that essentially we need the derivative over here to be less than 1 so that the solution actually converges linearly. Sometimes you're going to have to, I think, choose something else and just make sure that it is less than 1. Otherwise, you might not actually get it converging that nicely. Okay, next method is our Newton's method. And this is one of our more fast converging methods. So with Newton's method, we have actually quadratic convergence. And what that sort of means is that our order of convergence is going to be 2, given certain conditions, right? So if x1 is sufficiently close to the simple root, if f is 2 times differentiable, then we actually get quadratic convergence. So some cases we don't actually have it converging. Again, what we're sort of doing here is this formula over here. So we're sort of actually using the derivative, and when it comes to computing using Newton's sort of method now, it can get a bit complex. Because also when you're dealing with a system of equation, you're going to be dealing with the Jacobian. And I think for those of you studying 2301, you'll probably be familiar with this sort of formula over here, and I might just write it like this. Xk minus the inverse of the Jacobian, I believe. Times this guy over here. So you might have seen this formula and used that formula in MATH2089. Yeah, so essentially we're just going to go ahead and follow this formula here. Oh, that's an awful highlight color for that. And what we might actually go ahead and do is for MATH2089 at least, being familiar with your Newton's approximation is pretty good because there tends to be a question that tests for that. And also in 2089, I do see a bit more like Newton and secant method questions as opposed to bisection and fixed point iteration questions. So this is a question from Math2089. It's a bit of an outdated question, but let's go through it. To find the root of a real number, let's implement Newton's method. So let's use Newton's method to help us find our cube root here. And essentially what we need to be able to do is we need to have our function f of x. That was one component of our formula here. And then we also have to go ahead and find the derivative of that function. So if we have a look at our f of x, we're trying to find the cube root. So essentially we can say, well, let's make x equal to a1 over 3. And since we want our function to equal 0, we can sort of just rearrange that and have f of x is equal to x. Okay, yeah, I sort of have on the next screen as well, but x cubed minus a. So down over here, so we're going to set our f of x to equal to this function here. And again, we have to find the derivative of that as well. And the derivative of a cubic, very straightforward. So we end up with these two formulas down here. Hopefully you can see that on the screen, but these two formulas here. And then it's really about substituting that into the formula. I might move on a bit faster just because I'm a bit wary of time. But essentially, if you go ahead and do the substitution and a bit of rearranging, you should be able to prove this formula down here. One other thing that you would need to be able to do is to use this formula here to compute certain values. Let's say if you're given our initial guess. So let's say if you're given x0, you might be asked to compute x1, x2, and x3. Again, you just do that by substituting that into the formula. Okay. Whoopsies. Let's just have a look at the question first. So also let's talk a bit about the convergence for Newton's method and sort of the idea that Newton's method doesn't always sort of converge in that sort of quadratic where, as we mentioned earlier, it has to fulfill this condition here. So you are given that f of x is equal to e of x sine of x minus 100, and that there's a simple root at 6.443. And if you use the starting value of x1 near this 0, what is the expected order of convergence for Newton's method? And what we know is that the function behaves well because e of x and sine of x are both continuous functions, and what that means is that our f of x is going to be very nicely behaved and it is going to fulfill this condition over here. And what that means is that our expected of order is going to be 2. Okay, next we're going to move on to the secant method. This time with our secant method, we're going to need actually 2 points over here, right? So approximate f of x by a line through these 2 points here. Again, also just substituting into the formula. And with our secant method, again, we also have a condition as well. But our secant method has order of convergence, what we call superlinear convergence, because it's between 1 and 2 of this value here. And if I'm right, that evaluates out something close to 1.618. Yeah, so what I might actually go ahead and do is I did prepare another question to actually talk about for order of convergence, but just for the sake of time, since quadrature, so numerical differentiation integration, as well as ODEs is quite important, and it's more assessed, at least in 2089. I might let Lockie take over again to cover those two topics. But also just one final note, which I meant to mention earlier with Newton's method, is for those of you studying 2301, also be familiar with how to prove the rate of convergence, essentially. Yeah, so so for those of you doing 2301, just make sure to revise. And again, it's a lot of sort of just brute force, writing out formulas, rearranging them, but using your Taylor expansions to prove various things using your, I should stop scrolling, so lost, using this sort of idea here. Okay. I will now pass over the stream to Lockie, if he is good with that.
Okay, so we've started again. Sorry for the delay. So we're going to be going over quadrature, which, like Anne said, is a lot of numerical differentiation and integration. So the I guess the big part of this, a lot of numerical differentiation at least, is based on Taylor's theorem. Um, so this is very important, and for Math 2301, so a lot of time in Math 2301, a lot of these proofs involving the error terms, for example, come from Taylor's theorem. So it's important that we know it well and are able to apply it. But essentially, this is just giving us the expansion of f of x plus h, um, and in terms of derivatives, and we have also this remainder term over here, which is based on this is the Lagrange form of the remainder term at least. And we just keep in mind that this z term is just some number in the range a to b. Okay, so another thing we need to look at is the condition for this to hold is that it's cn plus 1 on ab. So what that means is it's n plus 1 times continuously differentiable. So that means we can differentiate it and the derivatives are continuous. So let's move on to looking at some actual quadrature. So the first thing we're looking at is approximating the first derivative of a function, and that is via the forward difference approximation. So the forward difference approximation is this thing here. It says that the derivative is equal to f of x plus h minus f of x divided by h plus some O of h term. Okay, so that's O of h term is something called a truncation error. Okay, which is related to Taylor's theorem. So I'll show you what I mean by that. We know that f of x plus h equals, well, f of x, f of x plus f dash of x h plus some terms that are all O of h. Okay, and you can see that by actually just rearranging here, we get our forward difference approximation. And notice that this forward difference approximation is very, very similar to what we have for just the definition of a derivative. Definition of a derivative, just ignoring that limit as h goes to 0. Now, there's something called a round-off error. What the round-off error is, it's related to the error involved with adding, subtracting floating point numbers, and it's related to the size of the machine epsilon. So this is the machine epsilon we looked at earlier. So that, again, reminder is the difference, or the smallest gap between two consecutive machine numbers. So the total error is the sum of the round-off error and the truncation error. So the truncation error is sort of just all those extra terms that we're leaving out. So that's all the terms leaving out in Taylor expansion. So now the next finite difference method that we're going to look at is the central difference approximation. So this is how we find the second derivative. Now, something I forgot to mention here is that the condition to be using this forward difference approximation is that it needs to be C2. Here it needs to be C4. Now, this central difference approximation also comes from Taylor's theorem. We just add the next level, we add the next level of expansion, f of x plus h equals f of x plus f dash of x h plus 1/2 f double dash of x h squared. So plus terms that are all O of h squared. So it comes from rearranging this and using our forward difference approximation. Okay, so we combine that to get our central difference approximation. Now in this case, the round-off error and the truncation error are almost the exact same, except now they're O of h squared, roughly. That's because all the terms that we're leaving out are all O of h squared. So now let's look at numerical integration now. So that's how numerical differentiation. Now let's look at approximating integrals using quadrature. So the main idea behind numerical integration is that any integral, right? Let's say the integral from a to b of f of x dx. Well, what does it represent? Well, it represents the area underneath some curve, right? Area underneath some curve. And remember our Riemann sums? Where do we actually get an integral from? Well, we know that the integral is the limit as a bunch of rectangles that approximate the area go to 0, or their width goes to 0. Okay, so what we're essentially doing is using the fact that what an integral is a special type of sum. So what we're going to be doing is approximating the integral as this sum here, this weighted sum of function values. So what this is just a bunch of weights multiplied by function values. Okay, what this sort of represents is a rectangle of sorts. Okay, but with varying width. So we can change the width, and the whole idea is that what we want to do is select these weights. So what is WJ? Select these weights in a way that minimizes the error and gives us the most accurate approximation. So let's look at some main, I guess, the quadrature rules that we'll be looking at. These are the trapezoidal rule, Simpson's rule, and Gauss-Legendre rule. Okay, sorry if I said that wrong. So in Math2089, what we're going to be, I guess in Math2089, these rules, what they are is essentially taking this weighted sum expression and using polynomial interpolation. Now, and the number of interpolated points will give us, when we go from trapezoidal to Simpson's rule. The rule that's sort of below trapezoidal rule is the midpoint rule that we're not going to look at here, but it's something that you should look at in preparation for your exam. Now, Gauss-Legendre is a bit different, and we'll see why soon. But yeah, so these three rules come from the Lagrange interpolating polynomial. So we sort of replace this integrand, right? Replace the integrand with a Lagrange polynomial that models it, and that sort of gives us a good quadrature rule. So now let's look at the trapezoidal rule in a bit more detail. So that's where it comes from in terms of Math2089, but the easiest way about thinking of the trapezoidal rule is that what we're essentially doing is taking the area beneath the curve and getting a bunch of trapeziums. Okay, so we're getting a bunch of trapeziums under finding the area of all the trapeziums and adding them together. So you can see in this case, by using just trapeziums, we've got a pretty accurate area underneath the curve. So the actual rule itself is fairly straightforward. It says that the quadrature of this function f is our h, which is our sort of step size, where h is a fixed value to be the interval divided by the number of trapeziums we're choosing to use. And then we have f naught, that's the original function value, divided by 2, plus the sum of all the other function values, plus fn divided by 2. Now, yeah. And in terms of our original definition of quadrature, in terms of weights, essentially what we're saying is that the first two weights are, the first weight is half, the last weight is half, and all the other weights are just equal to 1. Except we have that h sort of factored out to the front. Now, in terms of the error is always going to be given by this, okay, where xi is some unknown on the interval. Now, in terms of Math2089, it's important to know where this comes from. It comes from something called the Peano kernel. I won't be going over this in detail here because of time constraints, unfortunately, but there are notes and resources for you to look into that. Now, yeah, again, it's important to know where that comes from. But essentially, for Math2089, we could just sort of take this for granted. This is our error, and it's related to the second derivative, as well as h. So notice that it's related to h squared. Okay, that means that the rate of convergence for this is actually O of h squared. Okay, which is because h is related to 1 on n, that means it's O of n to the, well, so O of 1 on n squared. So as we change h, well, it is related to the square of h. Now, in terms of degree of precision, this is in Math2089. I'll just briefly go over what degree of precision means. Degree of precision means that our quadrature rule is exact for polynomials of the form x to the r up to r. So I'll say that again. What we want is that the quadrature rule is exactly equal to the integral, so we get an exact answer, the error is 0, up to r. So essentially what's going on is, for example, when it comes to the trapezoidal rule, if I check the function 1, so the constant function 1, what I get is exact. Okay? And I can check the function x, what I also get is something exact. But if I check the function x squared, I no longer get exact. So that means it's the highest power of a polynomial that it can exactly model is x. That means its degree of precision is just 1, because that's x to the power 1. So now let's look at Simpson's rule. So in terms of understanding what it is, it's sort of approximating the function as a bunch of parabolas, okay, and summing up the area underneath each parabola. So you can kind of see where this whole Lagrange, replacing the integrand with Lagrange comes from, because with trapezoidal rule, what we're doing is replacing the integrand with a bunch of straight line segments, right? And that gets us our trapezoidal rule, because the area underneath those straight line segments is the area of a trapezium, right? But in this case, what we're doing is we're replacing it instead with an extra, we're adding sort of an extra degree to that Lagrange polynomial, interpolating polynomial, and now we're free to have x squared, which is a bunch of parabolas. So we model the curve as a bunch of parabolas, and then find the area underneath each parabola, and then add it all together. And so the rule is given here. So it's a bit harder to memorize, but again, we have all the rules, all the information here. You can see that the weights will be given by this. Now the error of Simpson's rule is now given by this. Again, that comes from a piano kernel that you have to look into. But you can see that it is now O of h squared rate of convergence. And furthermore, its degree of precision is 3. That means that the quadrature rule is exact for polynomials, it's exact for q of 1, q of x squared, and q of x cubed. So it's exact for all of these. Okay, so now let's look at the last rule, which is our Gauss-Legendre rule. So the thing, I guess the reason why this is a lot different is that we're no longer doing this Lagrange polynomial method. We're doing something different. Specifically, what we're doing is, if we're looking at integrals over the domain -1 to 1, we can give it this rule. So wj f of xj. Now, how we actually will be picking these points no longer equally spaced. So something to note is that with these rules that we looked at, trapezoidal rule, Simpson's rule, midpoint rule, etc., what we're doing is we're having equally spaced points. However, with the Gaussian quadrature, we're choosing these points a bit more complicated. In fact, there will be the zeros of this polynomial of degree n. But the reason why we do that is because for the same amount of points, right, we can now get a degree of precision that is 2m minus 1. So, for example, if I used m equals 2, which is a very common type of, very commonly used quadrature, then I get degree of precision 3, whereas for even Simpson's rule, I would have to use more points to get that. So it's a bit nicer in that sense. Now the weights, and so essentially the weights and nodes are found using this special type of polynomial. So we won't have to know exactly how they're calculated, but we can see that for 2-point Gaussian quadrature, the weights are equal to 1, and these points are negative 1 on root 3, 1 on root 3. And again, these come from the roots of that polynomial. So now we can see that it is sort of a bit more complicated looking at this error term. As n goes to infinity, we get this is the error. It's approximately pi on 4 to the n. And again, this is our error, very similar to what we looked at for the Simpson's rule and so forth. Now, to keep in mind, all of these quadrature properties, we're assuming that the integrand is smooth on the interval. And you can see that for trapezoidal rule, we need to assume that it's twice continuously differentiable. For Simpson's rule, 4 times continuously differentiable. And for Gaussian quadrature, we are assuming it's 2n times continuously differentiable. Now, something to keep in mind is that quadrature will break down with unbounded derivatives. So if we look at the integral of root x, for example, we know that root x actually is not differentiable at x equals 0. Okay, and that's going to cause a lot of problems if we just try to use quadrature on this. We're actually going to get incorrect answers. So the solution to this is we must substitute. So we must perform a u substitution. So we can say let x equal u squared, for example, and that will sort of delete the error that we're getting from the unbounded derivatives. So one thing to note is that Gaussian quadrature only works from -1 to 1. That's to do with the fact that we're finding those points using the Legendre polynomial. So we're actually going to have to perform a bunch of transformations if we actually want to use Gaussian quadrature. So we have to perform this sort of substitution here to transform it. Now, some tips for difficult integrals. Unbounded derivatives apply change of variables. Discontinuity, we need to split the integral. If it's highly oscillatory, then we require a special analytic method. Narrow spike is we need to underestimate or overestimate the spike. So these two are probably a bit probably won't come up, but it's good to keep that in mind. So now we're going to be moving on to ordinary differential equations, and this is our numerical methods used to solve ODEs. So first of all, just a reminder from first year that an ordinary differential equation is some equation that involves a function and its derivative. First order means that the highest order is 1. So what we have is an initial value problem. So what an initial value problem is just an ODE with an initial value that allows us to solve it and sort of evaluate all the constants we need to just get an initial value. So to get a actual function not involving arbitrary constants. So now an ODE has an IVP, an initial value problem, has a unique solution if this is a continuous and bounded function, as well as this. So just to, I guess, revise, dy dt equals f of ty, okay? So what we're having is an ODE that's involving a function of 2 variables, t and y. So an example might be y dash equals t squared y, for example, or t squared y plus ty or something along that form. Now, when we have a bunch of ODEs, or even a second order differential equation, as we'll see, we can write that in terms of a system of only first order differential equations. So what it means for it to be a system is we have some function x that's a vector valued function. So it may be, x squared plus 1, x, cos x, something like that, sine x, something like this, and then we can actually, well, solve it because it may be a differential equation. We may get something like x dash equals, x1 times t, something like that. We'll see an example soon. So now let's look at some numerical methods actually used to solve ODEs. So the first one and most commonly used is Euler's method, and it's also the easiest to implement. So let h be the total time, or the final time. So remember, we're looking at some interval t0 to t max. assuming t naught equals 0, what we're going to get is h equals t max divided by n. Now, Euler's method is essentially to solve the initial value problem using this process here. So we're saying yn plus 1 equals yn plus h multiplied by f of tn comma yn. So in terms of intuitively understanding this method, it's essentially using the fact that the function f evaluated at tn yn sort of gives us the gradient at that point. Okay, so what we're using is the fact that, say we have this, so we have some point here, so that's yn. What we're sort of doing is saying that the point yn plus 1 is exactly just h times the gradient, where the distance here is h. Okay, while that may be slightly, and that sort of gives us like maybe some process that looks like this. Now, there may be errors involved. Specifically, the error is O of h. Okay. Now, we can also use an implicit Euler's method. So an implicit Euler's method is now, instead of it being in terms of tn and yn, so you can see that this is a recursive process. Like once I found yn, then I find yn plus 1, and then when I find yn plus 1, I can find yn plus 2, etc. But with the implicit Euler's method, notice that I have a yn plus 1 in terms of yn plus 1 itself. So what we're going to actually have to do to apply an implicit Euler's method is solve a nonlinear equation. And as Anne covered in her section, we can solve nonlinear equations using Newton's method, secant method, that sort of thing. So we can see that this method is maybe a bit harder to implement, but the advantage is that it's very useful for stiff ODEs, which is relevant in 2301. I'm not sure about if stiff ODEs come up in 2089, but essentially a stiff ODE is one that sort of changes or oscillates a lot when there are small changes. And the implicit Euler's method sort of handles the stiff ODEs a bit better. So now let's move on to the next, or a bit more of a more powerful numerical method. That is the Runge-Kutta method. So all of this stuff here comes from 2301, and this is sort of what Runge-Kutta is. So with Runge-Kutta, what we're doing is we're defining these psi variables, okay? And we have this big complicated formula here. But in general, this new value is only going to be up to 4 that we're going to be practically using. So what we'll be getting is only 4 different psi values, so psi 1, psi 2, etc. So we can calculate, or not calculate, but write expressions for all of them. And then the actual solution to the ODE will be given by this thing here. Now, what we have with this expression is a lot of random constants, right? Like what is Ci, A, nu, I, Bj, that sort of thing. When we didn't have like such a complicated expression for Euler's method. Well, the reason why is because Runge-Kutta is a very generalized idea. It's almost a generalized Euler's method in a way. And these constants are always chosen to minimize the error. So these constants will have specific values when we apply certain variations of Runge-Kutta, and they will all be chosen in a way that makes the truncation error O of h to the power nu. So for example, if we set nu to equal 4, then what we'll get is O of h to the power 4, which is a lot stronger than the Euler's method, which is O of h. So let's look at some actual Runge-Kutta methods that are used. So two-stage Runge-Kutta is when we set nu equals 2 and solve for some particular values of A, C, and B that minimize the error. So in terms of MATH2089, these values A, C, B come from something called the Runge-Kutta tableau. So the tableau will look like this. That's B, I think that's C transpose, that's A. I'll just double check that's correct, but I think that is. So A is actually a matrix, right? So we can use that to help us out. And yeah, so with a particular tableau using u equals 2, what we have is this RK2, or commonly used Runge-Kutta method. And this is sort of the expression that you'll be using a lot in Math2089. What this really is, like what Runge-Kutta really is in this case, how we can think about it intuitively is instead of, this is the other way around as well, sorry, that's B transpose C. What it really is instead of using sort of with that Euler's method, we used, one gradient to find the point. What we're doing is we're using one gradient here, there's another gradient there perhaps, and then we're finding a linear combination of these two gradients or weighted sum of these two gradients that gives us a correct answer or a very close answer that has minimized error. So we're sort of finding, so we have 2 points and we're looking at all the gradients in between, because the function may change a lot. And if we only use one gradient, there could be a lot of error involved with that. So Runge-Kutta with the RK4, we're actually using 4 different gradients. With RK2, we're using 1 gradient. So now let's look at a question to apply this in practice. So the motion of a damped mass spring system is modeled by this initial value problem. So what we have here is a second order differential equation, right? We saw that these Runge-Kutta methods and the Euler's method were only capable of handling first order ODEs. However, we can actually make this second order differential equation a system of first order differential equation. Okay, so how do we do that? Well, we want to first, write it as some system of first order differential equations. What we have is, so we have particular values. We have 5y double dash plus 2y dash plus y. Okay, so what we can do is do a sort of trick of sorts that helps us out. And that trick is setting y1 equals y and y2 equals y dash. So if we sort of do this transformation, what we can see is that actually because we're using x here, I'm going to use x just to make it a bit easy for us. So x1, x2. What we can see is that x1, x2 equals y dash. Now what we want to find is x dash, right? So that's y dash, y double dash. Now, what is y dash? That is nothing but x2, right? What about y double dash? Well, we can actually rearrange this equation. If we rearrange this, we get y double dash equals negative 2y dash minus y over 5. Okay, what's y dash? That's x2. So it's negative 2x2. What's y? That's just x1. And then what we get is this. So this is actually our system of equations. Okay, so you can see that this is some function of t and x1, x2. Obviously, there's no t in this particular example, but there could be in other examples. So the trick that we sort of need to remember is this x1 equals y, x2 equals y dash trick. And that can help us out. Now, if we wanted to use Runge-Kutta, let's say Runge-Kutta 2, just to make this a bit easier for us, with a step size of 0.1, what we can do is we know that h equals 0.1, okay, and we only want to do one iteration. We only want to do one iteration because we're starting from 1. The reason why is because you can see that our initial condition, oh sorry, I forgot to write the initial condition. You can see that our initial conditions are in terms of 1. So the initial condition of this particular system is going to be x of 1 equals 1, negative 1. The reason why that is because x of 1 equals y of 1, y dash of 1. And you can see clearly that we have expressions for y of 1 and y dash of 1. That's coming from our initial conditions. So we're going to get 1, negative 1. So what we need to do is just apply range cutter 1 and range cutter 2. And to do that, what we're going to be doing is using these particular values. So K1 is just evaluated. K1 is just f evaluated t of n, y of n. In that case, it's just going to be equal to 1, negative 1. And then K2 equals this f of tn plus 2/3 h, then yn plus 2/3 h k plus 1. So we know that the t part has 0 effect. Oops, just gonna do that. So that's tn. I think that's correct. HK1. So to actually do this, well, notice that we can sort of just use the fact that we can do x1 plus 2/3 hk1, which is just 1, and then x2 plus 2/3 h k1, which was negative 1 for the second. So if we did that, then we could sort of plug it into our calculator and get a value using range cutter 2. So that's sort of how we apply these numerical methods, but it's a lot easier to implement algorithms that do them, for example, in MATLAB. So we're going to briefly overview other methods. So one is the trapezoidal method. Another is Hyun's method, which is here. And what we can also look at is multi-step methods. So that's Adams-Bashforth and Adams-Moulton. Again, very important that you look over these, especially for Math 2 and how they work in a more theoretical sense, rather than just doing calculations. But again, in the interest of time, we will be moving on now to PDEs for Math 2089. So I'll be handing over to Anne to finish it off.
Okay, I think we've successfully transitioned again. So unfortunately, we are running a bit over time. I would love to spend a bit longer on PDs. Now, just a bit of a disclaimer: PDs is a Math 2089, so engineering specific. So for those of you who are, tuned in for Math 2301, this isn't going to be relevant for you guys. So we've already covered everything that should be in MATH2301. Um, Now, in that sense, I guess this is the first time we've actually run the combined MATH2089 2301 workshop, which is, why perhaps the timing didn't work out. For anyone, I'm just going to, put this out here now. For anyone who wants a bit more help with Math 2089, we do have former workshops um, on our YouTube channel. And because in those workshops it was sort of focused exclusively on 2089 in those 2 hours, some of them had a bit more opportunity to actually go in more depth in certain trickier questions. So I'm pretty sure we have one from 2021 that you'll be able to access on our YouTube, which is really good, especially if you want to look at PDEs in a bit more depth, and see some work solutions for that. Unfortunately, because of time, I'm not going to be able to cover a lot of it. I'm probably not going to go into the example, but I'll talk about it briefly. And with PDEs, I think for the exam, there tends to be the final question does tend to be a PDE question. So yeah, what we're dealing with now is instead of our ODEs, which Lockie just covered, we're now going to be dealing with partial derivatives. I'm just sort of going through it quickly. The types of PDEs that you would need to be familiar with. Oh, okay, yes. I was just checking the comments. Yes, thank you as well. The types of PDEs that we need to be familiar with are our elliptic, parabolic, and hyperbolic PDEs. And all of our PDEs are going to just have this form over here. Not all of our PDEs, but the ones that we're sort of going to be looking at in this course, so our second order quasi-linear PDEs. And essentially, they're going to be elliptic if we have these various conditions, right? So how we go about applying our numerical methods to PDEs is going to depend on what type of PDE it is. So I think we're going to start off with elliptic PDEs. And I'm sort of just going to go through the theory somewhat fast to an extent. And again, if you want to look at this in a bit more depth, I'd probably just invite you to have a look at the other seminar, unfortunately. Unfortunately, we did run out of time here. But with elliptic PDEs, what we're going to do is we divide our x interval and our y interval by n+1 and n+1 respectively. And then we're going to use our central difference approximation at each of these grid points. And you guys should be given a table of these, if I'm right, for your exam. If you do quite a bit of questions as well, you can sort of start memorizing these as well. And essentially the idea is you are going to use these approximations, and then you're going to take the approximation and you're going to substitute it back into the PDE that you're solving. And that's the general sort of procedure that all of these are going to take. Now with your parabolic PDEs, we have two methods, well, kind of three methods. One being our explicit method, and then also our implicit method, and then finally we're sort of combining that together. So let's have a look at the explicit method first. What we do is we take the forward difference approximation to the time derivative. Again, since it's a time derivative, we're really looking at that first. Mind blank. That first derivative here. Yeah. And our central difference approximation to the space derivative as well. And this time, we're going to be looking at our second order derivative, and we really get that because we're dealing with a parabolic PDE. Again, if you go ahead and substitute that into the PDE, this is the sort of equation that you're going to get. And I guess I am sort of going through it quite briefly, because to some extent it is just a lot of general algebra and just substituting and rearranging things around. Next one is our implicit method. So this time we're doing backward difference approximation, and this is now going to be the approximation that we use. Again, we do have our central difference approximation with space derivative, and then we're going to do the same thing, substitute that back into our PD. This is the equation that we obtain. And as I mentioned earlier, the final method is our Crank-Nicolson method, which is where we actually go ahead and take the average of our explicit and implicit methods, and we obtain this sort of not too pretty looking formula over here. Essentially just averaging our explicit and implicit methods. And the good thing about our implicit method and our method 3, even though they're, computationally a bit more difficult, is that they are unconditionally stable, whilst with our explicit method, we actually need this condition to be true. So that's why, and I think we can also see it from the ODE section, but our implicit methods do tend to be a bit more powerful. And finally, we have our hyperbolic PDs. Again, sort of same process. So we're going to use both central difference approximations to both our time and space derivative. Again, because it's hyperbolic, we're going to be dealing with our second order derivatives. And then same process. This is the formula that you guys get. And yeah, so I think what I wanted to do was to run through one of the past problems on PDs. Now, I personally don't think I'm going to be able to get through that in a timely manner. And considering we are already a few minutes over time, I'm going to go through this example here really briefly. It's just a general procedure of like what a final question tends to look like. And in the other tests, you'll sort of just have to apply, either sort of one of these methods here, and they'll tell you what. So like in this question, we're looking for a forward time central space scheme, an explicit method. So in that sense, like you just follow the whichever procedure it was. Yeah, so over here, I've got just a few formulas written out. So if you sort of just examine it, we get these formulas, and then we're going to rearrange that to get this formula here. And that's the general sort of way that we go about solving our PDs. So I think what I'm gonna just leave off with, let me have a look actually. Hold on. Yeah, so sort of just looking at the past questions for 2089. Also just being familiar with sort of like boundary conditions and all of those. I think I've mentioned this a lot at this point. For the sake of time in this seminar, I think I'm going to end it off here. What we might do, and also just check that that's all right. What we will do is all of these slides will be uploaded on the MathSoc website. So if you'd like to have a look at these slides, in the MathSoc website, which is, you can just search up UNSW MathSoc, there's a tab for resources, and under revision seminars, you can find all these slides to this year's seminar, as well as the seminars from previous years. And if you want to have a look at sort of these questions in a bit more depth, feel free to go ahead and do that. And I also invite you just to have a look at the 2021 2089 seminar. Um, and so we just skipped through because I believe that seminar, because it was just 2089, we managed to focus a bit more on like solving actual questions as opposed to just going through the theory. Other than that, I don't think I have anything else left to cover. So I might just go ahead and end the stream. Yeah, then. So yeah, thank you everyone for coming. Okay, going to be ending the stream.